Yeah, we are going to discuss converse of electric field produces the magnetic field. That is nothing but the varying magnetic field going to produce the electric field, or the varying magnetic fields produces the currents. How it is? Till now, in previous lessons in magnetic effects of electric current, we have studied that Orested has found the current when found the magnetic field when current flows to the uh, wire. Due to that, perpendicularly or around the wire, we found the magnetic field. The same manner here, when there is a change in the magnetic fields, due to change in the magnetic field, currents also produced. That is a converse statement to the previous current carrying conductor produces magnetic field. So that is possible. Is that possible? Is a question. It was a question because in this electric and magnetic fields, there was a scientist Maxwell. He is trying to do unification of electric field and as well as magnetic field. There were a thought for Henry and Michael Faraday. These two scientists were independently was thinking about this, and why won't the converse state? Converse is not possible. They used to think, and finally they thought and they invented experimentally. They found that experimentally how the converse is possible. With respect to Michael Faraday as well as with respect to Henry, it is possible. Let us, before discussing the Michael Faraday and Henry experiments, we need to know that what do you mean by electromagnetic induction? We have studied electrostatic induction, right, in previous classes. Now, what do you mean by electromagnetic induction? Electromagnetic induction is nothing but by varying magnetic fields producing the electric currents in its vicinity. Okay, then this phenomena is called as electromagnetic induction. Electromagnetic induction, or by changing the magnetic flux, we are inducing the field or a current in the neighboring coils or neighboring objects is called as electromagnetic induction. If we go a little more further into this topic, first, the most important role which plays by magnetic flux. What does it mean? What do you mean by magnetic flux? Magnetic flux means what, especially? What do you mean by magnetic flux? We studied earlier classes electric flux also, and the same manner we need to know here magnetic flux. A group of magnetic field lines passing through passing through unit area unit area its normally to its normally is called as magnetic flux. A group of magnetic field lines is called as flux. This flux, if it is passing through unit area in normal to the area, then we can say it is as a magnetic flux. See, let us see here. This is a area which I have taken and ds, and the unit vector which describes the direction of the face of the vector. Are you following? This
Yes,
is
sir.
a direction of the face of this area of vector. Okay. Now you can see here, this is a magnetic field B is nothing but the amount of field which is entering, the field lines which are entering through this area. Okay. And next, with respect to this area in the triangle component, if you consider, then this we are taking as hypotenuse, we can call it as if this is B, in the sense B cos theta direction is that. So when we are discussing in a small amount of flux d pi equal to product of magnetic field into r through the unit area ds is equal to b dot ds, we can write, that is in the direction of n cap. Now Direction of ds is along the normal to the surface and n cap is a unit normal vector. Therefore, d pi equal to b dot ds cos theta. D pi equal to b dot ds cos theta. Now you can write it is as a pi equal to b dot a equal to b dot a dot n cap, right? B dot a equal to b dot a dot n cap. This n cap is a unit vector which denotes the direction of the face of the area. Okay. Now this is for the complete flux to the area we are discussing. Here ds is a small unit area we have discussed. Okay. Now cos theta is the angle which varying with respect to the direction of the magnetic field and the facing of the unit vector n cap is nothing but it gives a cos theta here. So this is the way the flux will move. Flux in the sense, for example, this is a surface area. I think you are able to see here in my hand.
Yes.
Through this area, if it is entered and if it comes out, then this is exactly the surface area I can say. Through this area, magnetic flux if it is entered, this is the facing of the area. Facing of the area as well as magnetic field must be parallel, then therefore maximum amount of flux can transfer or moves to interior. But the area is like this, flux is moving like this. This is a perpendicular to the face of vector. So in this case, the flux is zero. The flux is not passing through the area there. Okay. So always it should be parallel to the facing vector n cap. Then the maximum amount of flux can pass to that. That we will write phi equal to b dot a cos theta. So always flux is positive whenever it is parallel to the unit vector and less than 90 degrees with respect to the magnetic field. Okay, as well as with respect to the magnetic field direction, it is if it is between the 270 degrees and 360 degrees also positive. But if it is perpendicular to the surface area or facing of the vector, then in such case it is zero. Flux is negative, obviously, if it is the direction opposite to the magnetic field, right? This is all about the flux. If you have clarity about this, then we can enter into the most important aspect is nothing but how this flux can change the or across a coil, how the flux changes comes, how flux varies. Okay. Coil in the sense, what do you mean by coil? Coil in the sense, it is a number of turns which is wounded around any material. Okay. Or number of turns is called as coil, we can call. Metallic wire, if it is having more number of turns, then we call it as a coil. The magnetic flux across the coil can be changed by factors we can see. One it is the strength of the magnetic field B, the area of cross section of the coil A, strength of the magnetic field obviously, and the area of cross section. If more area is there, then more changes comes. The orientation of the coil with magnetic field theta, the orientation of the coil with magnetic field theta, any of the combination of the above means the strength of the magnetic field B, the area of cross section A, the orientation of the coil with magnetic field theta, or any of the combination of the above means any of the combination of the above in the sense either both, for example, strength of the magnetic field area, and if it is angle also changes, the amount of flux transferring through that also will change, right? So these are all factors affects the flux around the coil. We know that magnetic field as well as area of cross section is vector quantities here. Area, since it is small elemental length, we have to take that is in terms of vector quantity only, small elemental areas. Because large area if you are taking that is scalar quantity, but small areas here in terms of fields and all when you are discussing, that is considered as vector quantity. Now, SI unit of magnetic flux is here, Weber or Tesla meter square. CZ unit of magnetic flux, Maxwell. Magnetic field is Gauss, remember. 1 Maxwell equal to 10 to the power minus 8 Webers. So, magnetic flux per unit area is called magnetic flux density. Magnetic flux per unit area is called magnetic flux density or strength of the magnetic field or magnetic induction. Next, Faraday's experiment, if you see how magnetic flux affects the coil. How magnetic flux affects the coil? See, you can see here, this is a magnet. This magnet, when this magnet moving towards the coil, look at here, what happens? Here coil in the sense, this is a coil is connected with the galvanometer. Remember, galvanometer is a device which is used to measure the V currents. Okay?
Yes.
So, either sides I am using the coils. I have used a magnet here. At a time we can observe two effects. This is by the south pole, this is by the north pole. By the north pole, what type of change comes here? By the south pole, what type of change comes here? We have to see here. Look at here. North pole in the sense magnetic field lines are moving inward, and south pole inward in the sense now from the north pole magnetic field lines comes out and moving towards the core. From the south pole magnetic field lines will go inside only, will not come this side. But it experiences around this some field. You can see now when the magnet moved towards one coil, and whenever it is moving towards this coil, automatically it is away from this coil. See, the magnet moved towards this coil, it became away. So first coil, let us see what happened. Here north pole is generated, here south pole is generated. The current direction you are finding here, anti-clockwise direction. As I said you in the clock rule in previous chapters, in the clock rule, what happened? The current which is facing here, if it is anti-clockwise, that gives the north pole, and if it is facing here anti-clockwise direction, then it is south pole. Okay, or south pole automatically. Therefore, with respect to that, here since the magnet has moved in this, you are finding some amount of current. Now see right hand coil, right hand side coil you are noticing, right? In the right hand side coil, this is a coil you are, it is finding that there, the current direction is opposite to the first coil. Opposite to the first coil in sense clockwise direction. Since it is clockwise direction, at this phase, at the right side face of the coil, if you see that is the south pole has formed, here north pole has formed. Remember, here also galvanometer deflected, here also deflected. Means both cases current has generated, but the generated current is in opposite direction. Due to the generation of the current, the poles has been given or poles has developed there. Poles has developed there. Okay. So now this is the north pole, this is the south pole, right? Now you can see in the same thing, whenever if I'll change the pole direction, means magnet if I reverse and place here, then south pole has come here. Then when the south pole has come here, what happens? It is completely current has generated same as, but the generated direction is opposite to the previous case, right? Same thing is happen in the right hand side coil also. So what happened here, you can understand that when there is a motion in the magnet, see, when there is a motion in the magnet, then only there is a current is flowing. Just magnet and coil are stable, therefore there is no change in the coil. Therefore, there is no change in the coil, and when the magnet moves, the current has produced in the coil. After moving, if it stops, the current also stops. But the magnet is supposed to move near or away. That's it. If it is moving near, the rate of change of magnetic flux will increases. If it is moving away, rate of change of magnetic flux decreases. But there is a change. What change? The flux linked with the coil has changed. Okay, that you can see here. See, in this, how this is a magnet you are finding here very clearly. These are the magnetic field lines, right? These magnetic field lines, when it touches this coil, then this coil is indirectly disturbing this magnetic field or magnetic flux. We can say this flux linked with the this coil. See here how it is. See, whenever it is linked with the coil, then only the deflection in the galvanometer. Means if there is a change only, the current produces there. If no change, no current. The change comes by the motion of the magnet, right? You finding? So
Yes, sir.
this is the way Faraday has done the experiment. So this we can say from this experimentation, Faraday has given one conclusion is that magnetic flux linked with the coil changes relative to the positions of the coil and the magnet due to the magnetic lines of force cutting at different angles, cutting at different angles at the same across cross-sectional area of the coil. Means whatever the flux is linking with the coil must be changes with respect to the relative motion of the coil or magnet. Okay. The when there is a change is taking place or when this flux is linking with the coil, automatically there is a some cut is taking place. Means magnetic field lines get disturbed. Okay. So due to this cutting or disturbing of the magnetic field lines which are linked with the coil is produces EMF. Okay, or current. Now the observation. What you have observed from this experiment, whatever you see. First one, if there is a motion only, there is a current. Means there must be a relative motion between the magnet and coil. Next, the induced polarities of magnetism in the coil. There must be some induced polarities of magnetism in the coil. Next, the direction of current to the galvanometer and hence the deflection in the galvanometer. The direction of current through the galvanometer and hence the deflection in the galvanometer, we have observed these all in the experimentation. Now, that the induced current is available only, whatever the current has produced only, as long as there is a relative motion, okay, between the coil and magnet. If there is no relative motion, obviously there is no production of current, there is no inducing current, right? So, that we found. Here, important point if you know down, coil can be moved or by fixing the magnet. Means in the experimentation we have seen only we have moved the magnet. No, it's not required. Magnet can be raised, coil also can be in the motion, right? Or both the coil and magnet can be moved, but there must be some relative motion or relative velocity between the coil and magnet. By that way, there is an inducing of EMF or current takes place. Okay, and while it is taking place, the magnetic flux linked with the coil is changes due to this relative position of the coil and magnet. If there is no change in the magnetic flux, there is no EMF induced. Remember, okay? Current and hence the deflection is large. Current and hence the deflection is large If the relative velocity between the coil and the magnet, if the relative velocity between the coil and the magnet, and hence the rate of change of flux across the coil is more, current and hence the deflection is large if the relative velocity between the coil and the magnet and hence the rate of change of flux across the coil is more. Means more deflection if you found and more current induced in the sense there must be more flux has been linked or more flux is linked with the coil. Then only there is a chance of more EMF or more inducing current takes place. Okay. Faraday's experiment 2. Till now we have done with the magnet and coil, right? Now we are going to do with this experiment same coil with the electromagnetic coil. When uh, electromagnet works when there is a current flow. How current flow will come? When a coil you connected with the external source or a battery, right? Now, external source or external battery I have connected here as a EMF you're finding here, right? Now, with this external source or external battery, what happens? The current flows to the coil takes place. Since current flows, what happens? Obviously, perpendicular to that, some amount of flux will generate. Okay, so therefore, it is acting as an electromagnet here. Look at it here. This is the primary coil. This is the secondary coil. This is the primary coil. This is the secondary coil. What is the difference between this? This is connected with the battery. This is connected with the galvanometer. Means this is acting as an electromagnet. This is just normal coil which is ready to induce the EMF or current in this. Now I'll turn on this switch. Then you can find here some changes. So the moment I turn on, what happened here? From positive to negative, the current flow takes place. Okay, so positive to negative, when the current flows takes place, when the current flow takes place, then what happened? Here EMF has induced. Look at here, the induced EMF always linked with the coil like this. See, to this coil, the flux as attached or linked, right? Whatever the flux as attached or linked with this flux will get cut or disturbed by this coil. Therefore, that leads to EMF induced in the coil or current induces in the coil. Remember here, when suddenly you on the switch, current rises. Here both are at rest. Remember, when you on the switch, then current flows. Suddenly the flux rises. When current you drops, I mean if you turn off, that time also EMF induces here, current induces. But after you on the switch continuously, the current flows, continuously magnetic flux supplies, but during that time no EMF induces because these two coils are at rest. Since these two coils are at rest, there is no inducing EMF. When there is a inducing current or EMF takes place, there must be a relative motion. What is that? Relative motion. There is no, if there is no relative motion, then there is no EMF inducing current also, right? But when you turn on the switch, suddenly EMF induces or rises here. You can see now the effect how it comes. Now, in this case also, suddenly if they turn off, when turn off also, Suddenly, when you turn off, here north and south poles are generated. Look at here. After that, it is disappearing. Why it is so? Because suddenly you off or on, here flux generates. The generating flux linked with the coil means while you are on or off, sudden rising, sudden disappearing is taking place. Means there is a change in the flux is taking place. If there is a change in a flux, then that is directly proportional to EMF or current in uses. Okay, if there is no change in the flux, let me, if there is flux is producing but there is no change, then no current will induce. No current or EMF will produce in the coil. See, the moment I on the switch, if I on the switch, the flux will produce, right? But the producing flux is linked with this coil. Due to linking, nothing will happen. When there is a relative motion, when there is a change, change, then only that produces current. Okay, the flux must be changed. Otherwise, there is no production of EMF or current. So this is with respect to the electromagnet. We have Faraday has done the experiment. Suddenly on the switch, there is a EMF induces momentarily. Current produces for a small interval of time, not for a long time. If you turn off the switch also, same situation. Because there is a change. See here. When the primary circuit is closed, current grows from 0 to maximum. Okay. Now you can see here, during this period, changing the current induces changing magnetic flux across the primary coil. But at the same way, the change in magnetic flux is linked across the coil, across the secondary coil, and induces EMF in the secondary coil. Whenever, if it is changing flux, if it is not changing flux, no induced EMF. Look at here, last point said. Induced EMF and hence deflection in galvanometer lost only as long as the current in the primary coil and hence the magnetic flux in the secondary coil changes. If not changes, no EMF induces. This is a Faraday's experimentation with respect to electromagnet. Means the question can come in the exam. Momentarily, if while on the switch, is there EMF generates? Yes, it generates momentarily, not for a longer time, right? And that you can see here. If you turn off the switch, yes, it generates EMF for momentarily, not for a longer time. See, when the primary circuit is open, current decreases from maximum value to zero. So during this period, there is a change in the current induces because of change in the magnetic flux across the primary coil. The change in the flux linked with the secondary coil induces current. If there is no change, no inducing current. Okay? These are the two experimentation done by the Faraday. After Faraday has done these two experimentation, he understood. Therefore, he proposed the Faraday's laws of electromagnetic induction from these two experiments. What he has done? He proposed two laws. That is, you can see here Faraday's law of electromagnetic induction. The first law, when there is a change in magnetic flux, when there is a change in magnetic flux linked with the circuit or coil, when there, remember the point, when there is a change in the magnetic flux linked with the circuit, and EMF and hence current is induced in the circuit. Okay, an EMF and hence the current induced in the circuit. Condition here. However, it lasts only so long as the magnetic flux is changing. However, it lasts only so long as the magnetic flux is changing. Okay, this will be there only until magnetic flux is changing. If magnetic flux is stopped, changing flux is stopped, then there is no induced EMF. Second law, the magnitude of the induced EMF, whatever EMF is inducing, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil in the circuit. Okay, rate of change of magnetic flux linked with the coil in the circuit. Simple logic I'll tell you. Take a spoon and put it in a water. If you take big spoon, then you are having of area of cross section more. Then you can disturb the more amount of water. More amount of water you can disturb because of more flux is attached. So more area of cross section is there for the flux, then more amount of water you can get disturbed. Same way in the coil also, area of cross section more in the sense large amount of flux can be we can change. If more flux also linked with that, then that leads to more EMF induces in the coil. Okay, so this is second law. First one is that whenever there is a change in the magnetic flux linked with the circuit, EMF induces or current induces. Hence, current induces. Okay, as long as it lasts until the magnetic flux changes. Now, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. That gives in terms of formula E. E means E stands for EMF. D pi. Pi is a flux. We know already. We have seen in the previous definition. Change in the flux with respect to time. D pi by dt. Okay. So therefore, E is directly proportional to d pi by dt. That gives E equal to k into d pi by dt, which is equal to d pi by dt. I can write that. I can also write E equal to pi 2 minus pi 1 by t. What is that? Pi 2 minus pi 1 by t means final flux minus initial flux by time interval. Of course, k is a proportionality constant here. This is about the Faraday's law of electromagnetic induction. So, this is all about the Faraday